Buffers is going to be the primary focus of this, but we're also going to talk about things like titrations and some polyprotic acids. So, to start off with, the idea of a polyprotic acid is something that can disassociate multiple protons. An example of this is H3PO4. Whenever you have H3PO4, there's not just one proton that can be disassociated, instead there's three. Now, H3PO4, or phosphoric acid, is considered to be a strong acid on the basis of the first proton. The first proton is one that disassociates completely, and that's what you see here when you see this rather large K value. The second and third protons are not strong acids, though, so you can't say the fact that if you have 1 molar H3PO4, you cannot say that that means that there are 3 moles of H+. Okay, it doesn't work that way because the first mole, or excuse me, the first hydrogen will disassociate completely, but the second and third will not. One of the things that you can recognize is the difference between K1 and K2. If you were to look at the K1 value, it's 7.5 times 10 to the minus third, and this is 6.2 times 10 to the minus eighth. When you divide those two values, you get 1.2 times 10 to the fifth, which is the exact same value you get when you take K2 and divide by K3. So that kind of tells you the likelihood of this disassociation to occur. Now, whenever you're expressing the likelihood of a disassociation to occur, we generally refer to it as K1, K2, K3, but oftentimes you'll see PK as well. Now, PK is going to be particularly important a little bit later. So whenever you look at it, remember, anytime you have a P in front of something, that just means take the negative log of. Just like POH is the negative log of OH, and pH is the negative log of H. When you have a PK3 or pKa or something like that, it just means take the negative log of K value. So, when we look at the relationship between Ka and Kb, a lot of times you'll be given a Ka value and asked to solve something involving a base. In the case of the Ka value, the base, or excuse me, in the case of the base, the Ka value is not worth a whole lot. So instead you need to be able to manipulate it to find the Kb value. And it's manipulated on the basis of this. Any Ka value for an acid or base times the Kb value is always going to equal 1 times 10 to the minus 14th. So if you're given a Kb, or excuse me, a Ka value of something like 6.3 times 10 to the minus fifth, and you're asked to find the Kb value, what you can then do is just say, okay, well that's 1.6 times 10 to the minus 10th because this divided by this. Now, where this becomes particularly important is when we're talking about titrations, which we're going to get into in just a second. But let's say, for example, that you have HCl and you titrate it with NaOH, and you're at what we call the equivalence point, which means these are gone and all you have left is NaCl and H2O. Well, you could use these in order to help figure out the pH, and we'll get into that in just a second. Now, realize that a salt can affect the pH of something as well. This isn't a great example because this example right here has HCl in it, and HCl is an example of a strong acid, so it would disassociate completely. But if you had something instead that was like CH3COOH, and then you had sodium acetate as well, realize that this right here would affect the equilibrium value. This disassociation of an acid comes to an equilibrium. That's why we have it a K value. Well, normally we would solve these with a Rice chart. Well, when you have a Rice chart, if there's no other substance present, then this value is a 0. But if you have some other salt to go with it, this is no longer 0. Instead, you'd have to say, oh, well, it's 0.15 molar, so this starts with 0.15. And then you would go through and solve it the exact same way. The problem is that you just don't have that initial value of 0. Okay, hydrogen would still be 0. But that's why you would get different values. So you'd get X, X. So you'd have X, and then you'd have 0.15 plus X. And so you get a little different value whenever you do that. So realize that the salt can affect the pH. You should also be able to explain this in terms of Le Chatelier's principle. If you increase the concentration of this whenever something is already at equilibrium, you've disturbed equilibrium. And so the system will respond to try and reestablish equilibrium. In doing so, it will try and get rid of some of that excess CH3COO, so it'll kick this reaction to the left. Well, in doing so, it actually decreases the amount of hydrogen ions that are in the solution, and therefore will affect the pH. So there are a couple of factors that affect the acid strength. Remember, the dissociation of an acid is what determines its strength. So if you have something like HCl, the reason why it's a strong acid is because it disassociates completely into H plus and Cl minus. Now, you would not expect that to happen whenever the bond between these two things is very strong. So whenever you look at these things, you're looking for weaker bonds between hydrogen and something else. So the reason why you have these particular um, patterns all has to do with the bonding with hydrogen. If you were to look at something like, and this obviously excludes the noble gases, but if you were to look at something like this, like you have fluorine, chlorine, bromine, and iodine, the acid strength increases as you move down those halogens. Now, the reason why is you have a larger electron cloud each time. Whenever you have the larger electron cloud, you have something that's more likely to take in a it's more likely to take in this hydrogen. It's not likely to be disturbed whenever you take in those extra hydrogens because it has more space, or those extra electrons. As you move across the periodic table, you have electronegativity increase. So it's increasing the likelihood that it can take those electrons on and leave a disassociated proton. Now buffers are systems that can take a large amount of acid or base without changing the pH. And buffers are really important, especially in life, because you have something called homeostasis that you have to deal with. Your body can't change pH very much, otherwise it will die. So the buffer system is really, really important in terms of biological systems. Whenever you have a weak acid and a conjugate base, or a weak base and a conjugate acid, that is how you set up a buffer system. Now, the example that they have with a buffer system here would be composed of C3COOH and CH3COO. So the buffer system involves those two things right there, the weak acid and the conjugate base. The advantage of the buffer system, if I were to add acid, that right there, the acid can react with the CH3COO and it can make a weak acid. Okay, well, in taking a strong acid like HCl and turning it into a weak acid, you've greatly restricted its ability to disassociate. Okay, likewise, on the other side, if you add a base, if you take a base and add it to a weak acid, remember the weak acid isn't disassociated completely, so the pH is, fairly, it's not very low. It's really high. So because of that, whenever you add the base to it, it's not going to change the pH that much either. So whenever you have a weak acid and its conjugate base, or a weak base and its conjugate acid, you can create what we call a buffer system. Okay, an example of a buffer system is the carbonate bicarbonate system, and this is regulated by your breathing and your kidneys. But what it does is it actually uses the CO2 that you have in air, and it can diffuse it into water. Well, whenever it does that, it turns into carbonic acid. And this carbonic acid also has bicarbonate and carbonate ions in it, which allows you to regulate the pH of your blood. Okay, the pH of your blood is actually slightly alkaline, so it can't move very much from that very set value. Okay, now whenever you calculate the pH of a buffer, it's really important that you use something called the Henderson-Hasselbalch equation. And that's this right here. It makes a little bit more sense if we write it out in this way. pH equals pKa plus the log of, we're going to write it out this way, A minus over HA. This right here is the Henderson-Hasselbalch equation. pKa is, the negative log of the Ka value. Generally, that's found in a table, or they will give it to you in a particular question. The trick to the Henderson-Hasselbalch equation is this ratio right here. How much A minus do you have and how much HA do you have? And that's generally found using a Rice chart. Sometimes it's a little easier than that, but for the most part, you're going to use a Rice chart in order to figure those values out. So an example of A minus and HA could be something like NH4 and H3. This would be your HA, and this would be your A minus. It could be something like it could be something like CH3 COOH and CH3COO. The trick is to identify what the conjugate base is and what the acid is. Once you have that, it becomes really easy. Now, this particular term is the reason why you have what's called the buffer capacity. Okay. So now it says how much NaCl should be added to a solution of 0.01 molar HCl to produce a pH of 3. And the answer is none. Okay, this cannot be done with a buffer solution. You could eventually do it by adding enough to dilute the solution, but this cannot be done with a buffer solution that is considered to be a strong acid. Whenever you have a strong acid and you use the Hasselbalch equation, you would get this. Okay, well, whenever you have a strong acid, this term essentially becomes zero. Whenever it becomes zero, the Henderson-Hasselbalch equation doesn't work anymore because it completely disassociates. Now, calculate the pH of a solution of ammonium chloride ammonia mixture if you have 1 molar NH3 added to 0.5 molar NH4Cl. So the first thing that you would realize, you say, okay, pH equals pKa plus log, and in this case it's going to be NH3 divided by NH4. Okay, that's my Henderson-Hasselbalch as I'm going to plug them in. So all I would have to do is I would have to look up this term in a table. The problem is you generally won't see a Ka value for ammonia. So instead you have to say, okay, I've got ammonia, which is NH3, which is a base. So at this point I'd say, okay, well, what's the Kb value? When you get that Kb value, you'd have to say, okay, well, the Ka is going to equal to Kw divided by Kb. Okay, once you do that, now you have the Ka value, and you can take the negative log of Ka, and you can solve for the pKa. Once you have that, you'd have plus log, and then you have your NH3 concentration divided by your ammonia concentration. Now the buffer capacity is really important because that's how much you can take in before you actually change your value very much. And the buffer capacity is determined by this term of the Henderson-Hasselbalch. Okay, now the reason why this determines your buffer capacity is it tells you exactly how much you can take in before you can change the pH very much. And here's what we mean. This term is very, very small compared to the other term. The pKa value is the primary determining factor when you're looking at pH. So whenever you're looking here, okay, these are the things that come into play before the other term comes in. So really you're looking for running out of stuff is what you're looking for. So a lot of times you'll see something like this. I have 2.0 and 1.0, meaning I have 2 molar A minus and I have 1 molar HA. So this could be something like acetic acid and acetate. The buffering capacity of this particular buffer is different for each value. For example, I could take in 2 moles of HCl without changing my buffering capacity very much. The reason why, this 2 molar HCl could then react with this A minus, and it could turn this term to 0. And it would turn all of it into 3 molar HA. My buffering capacity isn't quite as large for a base, and the reason why is I have 1 molar HA. So that means I only have 1 mole of NaOH able to react. Okay? When you exceed these values, when you exceed the values at which the A minus or the HA is there, you will start to change the pH because you're adding a strong acid or a strong base that is no longer buffered. So when you run out of this, it's called running out of the buffer capacity, and then you would take, instead of changing to Henderson-Hasselbalch or anything like that, you would just calculate. Next, we need to talk about the titration. The titration is a really useful chemical technique that is used in acid bases in order to figure out unknown concentrations. It's also used in precipitate reactions. Basically, a titration is when you take a known value and you use it to calculate an unknown. For example, this right here can be an unknown. And what I can do is I can add, either if this is a base, I can test it really easily with litmus paper or something like that. I can add set amounts of known acid until it reaches what's called an equivalence point. Now, whenever we look at acids and bases, we're looking at the reaction between them. That's called a neutralization reaction. A neutralization reaction is governed by the fact that you have this. You have H plus OH goes to H2O. That's why it's called a neutralization reaction. But that's a simplistic view of it. Not only do you have H plus plus OH goes to H2O, but you're also going to have a salt that's produced as well. So this right here is the titration technique. The titration technique is governed by the idea that you can use this. The number of moles of acid equals the number of moles of base. That right there is the same thing as you have for the dilution equation. The dilution equation just says, hey, here I've got a whole bunch of something, and here I have that same amount of something, but I added a bunch of water to it. So the number of moles is the same. That's the basic idea that we have here. The number of moles of acid equal the number of moles of base, and that's why it's called the equivalence point. So when you have the number of moles of acid equals the number of moles of base, remember there are other ways of calculating the number of moles. The primary one being molarity times volume. So you have the molarity of the acid equals the molarity of the base times the volume of the base. This right here is very, very similar to the dilution equation. The only difference is in the dilution equation, instead of doing a reaction, you're simply adding water. Now, whenever you do a titration, generally what you'll use is you'll use an indicator. An indicator is a substance that will change color when its pH reaches a certain threshold. And you see that right here. You have something that starts off red, and that's probably because it's very, very acidic. Then, as you add NaOH to it, the color changes. And it changes when it hits a certain pH. Each indicator has a different range for these. Some indicators will only change color once, while others will change color multiple times. So you have to be very selective in which indicator you're going to use when you're examining different acids and bases. So, the next one, you have a color change that's right here. For example, this pH could be like 2, and this pH could be 6, and this pH right here could be 8. Those things are what you're generally looking for. Now, pH, not a pH, but a color change can indicate an equivalence point if you select the right indicator. Now, the equivalence point is a lot easier to see whenever you graph them. And one of the things that you can do is you can graph the volume of the base added and the pH. Whenever you do this, you create this titration graph. Now, the titration graph is something that you will see on the AP exam. Okay, whenever you look at this part right here, where you have a dramatic change in pH, that right there is when you are approaching the equivalence point. You may have noticed when you were doing your acid-base lab that it is very, very difficult for you to actually find this the equivalence point. The reason being is the pH changes drastically in this narrow region. The equivalence point is where it starts to change. It's halfway between where it starts to change and where it ends its change. Now, the equivalence point is defined as moles of acid equals moles of base, and for a strong acid, strong base is assured to be 7. The reason for that is you have HA goes to HA plus BOH, you're going to produce BA plus H2O, so some sort of salt and then water. Because of that, you're going to have a pH of 7. So that's what you're generally looking for when you have a strong acid and strong base. Those values will change if you have a weak acid and a strong base, or a strong acid and a weak base. It will shift those equilibrium, or it will shift that equivalence point value, the pH at that particular point. Now, when you are doing a strong acid, strong base titration, the initial pH is determined by the concentration of the acid. So let's look at this. Let's say that I have 0.15 molar HCl, and I have 50 mils of it. 50 mils of 0.15 molar HCl, and I am titrating it with 0.1 molar NaOH. When I'm doing this titration calculation, the first thing that I want to do is I want to find the equivalence point. Because the equivalence point, where I am at this thing, will actually be determined how I calculate the pH at a given point. So the first thing that I would do is I would find the equivalence point. I'd say moles of acid times volume of acid equal moles of base times volume of base. So 0.15 times 50 equals 0.1 times VB.
Whenever I get my calculator out and you actually do this calculation, one of the things that you're going to realize is, hold on a second, just made a mistake, 0.15 times 50 is 75 mils. So my equivalence point is 75 mils. The first thing that I do is my initial pH. My initial pH is determined by the concentration of the acid. Before I add any base, the pH can simply be determined by pH is equal to the negative log of 0.15. Now the reason why I can do that is because this is a strong acid. Since it's a strong acid, it dissociates completely. So 0.15 molar HCl means 0.15 molar H+. Whenever I put this into my calculator, I would take the log of 0.15, and you end up getting a value of 0.8, we'll call it 2. So that's the pH initially. Now, um, as I start to add base, what I would do is I'd say, okay, as I add base to it, I would expect the pH to increase. So by how much? You have to figure out this before the equivalence point. You'd say, okay, well, how many moles of acid minus how many moles of base divided by the total volume. In other words, I'm going to have more moles of acid to begin with. The easiest way to keep track of this thing is with a rice chart. You'd say, okay, I have HCl plus NaOH goes to, and then it doesn't matter on the other, it's just B, or it's NaCl and water. Okay, now initially I have, and this is where you have to be very, very careful. You want to do this rice chart, you want to do this one in moles so you can keep track of everything. So I have 7.5 millimoles of HCl. This is really hard to see. Next, I have, pick a volume. If it's before the equivalence point, let's say it's 50. Okay, if I have 50 mils, that means I have 5 millimoles of NaOH. Okay, now I can figure out the change. These two things react completely, so I can identify the limiting reactant. The limiting reactant in this case is sodium hydroxide. So I would subtract 5 millimoles. When I subtract 5 millimoles, and what that means is I end up with 0 sodium hydroxide, but I only have 2.5 millimoles of HCl. Now, this is why it's really important that you do these calculations in moles, because molarity is moles divided by volume. I now have 2.5 millimoles of HCl. So I have 2.5 millimoles of HCl. But the total volume changed. I no longer have 50 mils as my total volume. I added 50 mils of base, bringing the total volume to 100 mils. So if I take millimoles divided by milliliters, that gives me my HCl concentration, and my HCl concentration would be roughly 0.025, and then that's my HCl. Once you know this, now you can say this will disassociate completely. pH equals the negative log of that, so you'd say log of 0.025, and you would end up getting a 1.6 pH. So, if you look, even though I added 50 milliliters of 0.1 molar sodium hydroxide, the solution is still quite acidic. Now, at the equivalence point, the pH is always 7. Now, once you exceed the equivalence point, this thing changes. The pH is now determined by the excess OH concentration. So I'm going to go ahead and erase this. We're going to look at it again as another rice chart. So if I exceed the equivalence point, let's say this time instead of adding 50 mils, I add 100 mils. Because remember my equivalence point was 75. So I say rice, and I know that I had HCl, and I know I had NaOH. Well, I still had 7.5 millimoles of HCl, but this time 100 times 0.10 is 10 millimoles of NaOH. So now the limiting reactant between these two things is HCl. So now I run out of HCl first. When I do that, I have 0 HCl left, and now I have 2.5 millimoles of NaOH. Now remember, the reason why we would do this in moles is because the volume changes. As a result of that, you can now take this and you can divide it by the new total volume, which is 150. because you had 100 100 mils of NaOH and 50 mils of HCl. As a result of that, you have 2.5 divided by 150 ends up giving you something along the lines of 0.017 molar OH. You can then calculate the POH from that, and then after that the pH. But this is how you do strong acid-base titrations. The idea of the rice chart is crucial to your understanding of titrations. Next, it says how much 0.15 molar NaOH is needed to be added to a solution of 25 molar, 15.8 molar HCl to reach a pH of 7. So the fact that you have a strong base and a strong acid and you're trying to reach a pH of 7 means you're trying to do the equivalence point. The equivalence point is determined by the number of moles equals the number of moles. So let's say 0.15 VB is equal to 15.8 times 25, and then you could solve from there. In the calculator, 15.8 times 25 gives you something like 395, which you divide by 0.15. You end up getting a rather large number. So the volume of base necessary would be something like 2.6 liters, or 2,600 liters, roughly. Now it says, what is the molarity of KOH if 73.2 mils of solution is added to 25 mils of 1 molar hydrobromic acid in order to reach a pH of 7. So once again, we've established the equilibrium point, strong acid, strong base. So we would say, okay, number of moles equals number of moles. In this case, I know that I use 73.2 moles of base, or excuse me, 73.2 mils of base. In this case, I'm trying to solve for the molarity of the base, which is the most common thing you do in a titration. In acid, I know I had 1, and I know I had 25. 1 times 25 divided by 73.2, you end up getting a concentration of the base. The molarity of the base is roughly we'll call it 0.34. Okay. The next one, it says a 15 ml solution of 2 molar HCl is titrated with 0.4 molar KOH. Find the pH at the following volumes. So remember, the first thing you want to do is you want to find the equivalence point. The equivalence point in this case would be the volume of the acid times the molarity of the acid, which in our case would be 30, equals 0.4 VB. So the volume of the base in this case would be 30 divided by 0.4, which would give us 75 mils. Okay, that's the equivalence point. Because of that, we're only going to do one of these as an example, and you can do the rest after that as practice. So you see HCl plus NaOH goes to, it's KOH. KOH goes to KCl plus H2O. Those are my reactants. The initial values that I have is I have 30 millimoles, and I have, my potassium hydroxide. I have, we didn't figure that out yet, did we? Oh yeah, because we have 10 mils. So 0.4 times 10. So I initially have 4 millimoles of KOH. Now, you can clearly see which one is the limiting reactant. It's going to be the KOH. So as a result, you lose all 4 of those. 30 minus 4 gives us an equivalence of 26. We have right here 0 KOH. On the other side, we do have 4 KCl's that are produced, but that is going to have a negligible effect on the pH because we have HCl as a strong acid. So as a result, you can now say I have 26 millimoles of HCl, 26 millimoles of HCl divided by my total volume. My total volume in this case would be my 15 original mils plus my 10, so 25. So when you take 26 and you divide by 25, you end up getting the new concentration of the solution, which is 1.04. That right there represents the molarity of the HCl that's left in the solution. In this case, you would say pH equals the negative log of 1.04, and you get something roughly close to, 0, or it's pretty close to 0, I think. So we'll do negative log of that, and we get 0.017. Okay, it's the exact same procedure for each one of these. The only difference is instead of 0.4 times 10 to give us our initial value, it'd be 0.4 times 20 to give us our initial value. So this value would change to 8, which would change everything else. Okay, when you have a weak acid, weak acid, strong base titration, the steps are very similar. You can find the initial pH, but since it's a weak acid, you can no longer just say pH equals the negative log. Instead, you have to use a weak acid. You have to use the Ka in order to figure out what the pH is. After you have the initial pH value determined by the Ka, you can figure out the pH before the equivalence point using the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation will take into account the buffering aspect of the weak acid and the weak base. The idea that you have some sort of A minus over some sort of HA. So that will account for the pH before the equivalence point. When you are at the equivalence point is where you have HA plus NaOH, and these things have completely canceled each other out. The only thing that's left is A minus and H2O. Now remember, this right here is our weak acid. So this right here is the conjugate base. So this here is actually something of a base. So when you take A minus and you have H2O added to it, it will produce HA plus OH. So this right here is actually something of a weak base. So at the equivalence point, you actually would have to use Kb in order to figure out what the pH is at a particular point. Now, after you have passed the equivalence point, excess NaOH, remember, sodium hydroxide is a strong base, so it disassociates completely. So once you reach that equivalence point and you go beyond it, the pH is determined entirely by the excess OH concentration. Now, this is probably one of the more difficult things that you'll have to do. So we will go over this in more detail in class. But basically you say pH is determined by Ka, Henderson-Hasselbalch, pH is determined by Kb, pH is determined by OH concentration. So it's one of those things that you can kind of get through. Now, if instead of having a weak acid and strong base, if you had a strong acid and a weak base, it'd be initial pH would be used determining by Kb. Then you would have Henderson-Hasselbalch. Then you have equivalence point would be Ka, and then excess concentration of H+. So it's one of those things that you have to get used to, but it's not incredibly complicated if you've learned the Rice chart by now. All right, the last thing is titration of polyprotics. It occurs stepwise. You titrate the first proton completely, and then the second proton, and then the third proton. And what you see here is you have this buffering range right here. And this was probably the most difficult thing for you in the lab, was recognizing that you had this equivalence point and this equivalence point were probably relatively easy to notice. But this middle one, this cell buffering range where it was undergoing a buffer capacity, is often hard for you to identify.